To understand anything, we must understand the basics. And the basics of time crystals starts with symmetry. So what is symmetry? When you think about symmetry, you probably picture something like this. One half of the tree is just the other half reflected along the line of symmetry.
This is a fractal and has multiple types of symmetry, including reflectional symmetry. As you can see, if we zoom into the image, we see the same image recurring over and over again, which means the fractal exhibits self-symmetry. As we look at these different symmetries, we can start to build a general definition for what a symmetry is. In physics, symmetries are a physical or mathematical feature that remains unchanged after any sort of transformation.
The most famous symmetry you probably would have heard of is the speed of light. No matter what frame of reference you observe light in, the speed of light remains constant. One more thing to know about symmetries in physics is that they are closely linked to the conservation of a quantity, such as energy or angular momentum. So what if symmetry gets broken? Now let's take a look at the glass of water.
Ice exhibits a crystalline structure which is represented by this model. As you can see here, ice breaks spatial and rotational symmetry because the water molecules prefer specific points in space. They can exist in these certain spots but not in between. Let's try another example. This is a solid wall. If you were to knock it here, it would feel more or less the same as if you were to knock it here. In this way, it exhibits spatial symmetry. This fence is different from the solid wall because there are gaps in the wood. An interaction with the wood is different from an interaction with the air in the gaps in the fence. In this way, it breaks spatial symmetry, because it's not the same at every point in space. In 2012, Frank Wilczek, a Nobel Prize-winning physicist, theorized something capable of breaking time translational symmetry. This symmetry states that stable objects in a closed system remain the same over time. In this way, the symmetry is closely linked with the conservation of energy. Energy is neither created nor destroyed. It's very hard to imagine time translational symmetry being broken, but let's give it a go. Let's look at the six-sided die. The probability of landing a 6 with this die is 1/6. This probability stays constant over time, and by that, I mean it doesn't change to become 1/2 at 2 o'clock on a Sunday, or 1/20th at 4 o'clock on a Tuesday. In this way, the probability of landing a 6 with this die exhibits time translational symmetry.
But that would seem obvious, right? There's no way probability can change at certain points in time, unless you were to change the shape of the die, and that would be cheating. That would introduce an exterior force into the system. Time crystals, like many other quantum phenomena, don't follow behavior that would seem rational to us. But we have to remind ourselves that the universe is under no obligation to follow our expectations or rationality. Time crystals have a property called quantum spin. For the sake of simplicity, we're going to represent the different values of quantum spin with different colors.
Wilczek originally theorized that time crystals would pulse back and forth between these values of their own accord, without the need for an outside force, but this was later shown to be impossible. The oscillation would be an example of perpetual motion, which cannot exist. However, if we change the rules just a little bit, say with the addition of a periodic laser pulse to influence the particles in the time crystal to start changing their spin, something interesting starts to happen. The time crystals indeed begin to oscillate, but they do so at their own intrinsic frequency, not the frequency of the laser pulse. Even if you were to change the frequency of the laser pulse, the intrinsic frequency stays the same. Because time crystals have some self-persistence of their state, they're shielded from external input to a certain degree. They have extra resilience to heat entropy and external vibrations. This makes them ideal to use in quantum computing, which requires protection from outside interference. One of the major drawbacks of quantum computing is the need for high-powered cooling systems. Entangled atoms in the crystalline structure of quantum crystals can store stable quantum bits, or qubits of information, at much higher temperatures, making them more practical and accessible for usage in the community. Quantum computing offers several advantages over classical computing in a few specialized fields. Eventually, we'll reach a limit in classical computing power and energy efficiency. Quantum computing could push past these limits. In addition, time crystals have applications in nuclear fusion, which is heralded as a savior to all our energy problems. By pulsing at regular intervals and remaining largely unaffected by external input, time crystals may be able to keep time with astonishing precision. This allows greater control of fusion reactions and may allow researchers to finally sustain nuclear fusion. It would be unsurprising if many more applications of time crystals are discovered in the future. Time crystals are at the frontier of the exciting field of non-equilibrium matter. We can't wait to see what lies ahead.